Okay, so this is a presentation as myself as head of the Geodesy Observatory of Tahiti. So up here, it's about 1 kilometer from here, we have the Geodesy Observatory of Tahiti. It's a structure that is maintained by, of course, the university here, but also NASA and the French Space Agency. So this presentation is done by myself and Lydie Sichois, who is, so say, the assistant director of OGT. Okay, so it's about millimetric geodesy and climate modeling. So it's not a presentation about results, it's a presentation about how we can model the climate from, data coming from geodesy. So it's a little bit probably not so well understood by people. So I will spend 15 minutes to discuss about what we need geodesy to constrain climate modeling. Okay, so basically you know that there is at the moment different scenario predicting by the end of the century a very large increase in temperature. So if you had a look at the news yesterday, we had an expert from the IPCC, Intergovernmental Panel on Climate Change. So it was published on the New York Times, and they call for better, understanding about how the climate change will hurt our life. So the IPCC is issuing different climate scenario, and their climate scenario are based on climate models. So here you can see that now the temperature is increasing, and the rate of the increase is growing. So by the end of this century, we can see that we have a global warming will affect several areas in the globe, and especially area in the north, and of course area inland like here Amazonia, Sahara, and other countries. So some areas will become wetter, others will become drier, but with an overall increase. And of course, there is countries that will lose in the process, lost some, agricultural lands, but there is also other countries that will beneficiate for this trend. For example, if you look at the projected agricultural productivity in the world, but you can see that some countries in the north, like Canada, Russia, Siberia, will have more, lands for crops and for agriculture. And of course, some other countries, basically the countries in the tropical areas, will suffer a lot. So it is very important to be able to predict the trends. That people have a tendency to ignore is that if we want to model the trends, you need data that are able to constrain on a global basis the trends. And it's not the temperature measurements that will be able to constrain the trends. Of course, temperature measurement, the amount of carbon dioxide gases and other greenhouse gases, of course, they are inputted in the models, but they are not alone. So we need to understand how we have transport of masses on the surface of the Earth. Why transport of masses? Because, for example, if you have a glacier, if you have ices melting in the poles, the masses will go in the ocean. So the ocean will rise. Okay, and we need to model this. We can have also some, I spoke about humidity agriculture. This means that in the north area, like Canada, you will have more moisture. So this means we have a shift of water from the tropics to the north or to the south. So we need to model this, okay? And this, there's a transport of masses are extremely important. We have a transport of masses at the surface on the Earth at different time scales. Of course, we can have very long time scales like tectonics is 100 million years of no interest for us, of course. But we can have, how to say, the melting. The melting is taking place in time scales of decades. Here you have a very interesting graph about all the possible scales that can be seen on the transport of masses on the Earth. So basically, we are interested for climate studies about transport of masses that are taking place from weeks to decades. Because if we want to predict the climate by the end of the century, okay, so basically is something like 8 decades from now. So we need to introduce this in the climate models. So I repeat again, climate models are not only about greenhouse gases, are not only about temperature, are not only about the carbon dioxide on the oceans. Of course, there are important parameters. We need to input them, but they are not alone. We need to input very large scale transport of masses. Here, you can see one of the main results provided by Geodesy using a satellite that is called GRACE, that was operating for nearly 10 years. And this satellite was, by looking at very small discrepancies in the orbit of the satellites, we were able to reconstruct the motion of masses on the surface of the Earth. And you can see here in orange color, there is, how to say, an increase of masses. In blue, there is, how to say, a lack of masses at the surface of the Earth. And if you compare the prediction here between the precipitation changes for the up to the end of the century, and here the transport of masses, you can see a very large correlation between how to say the transport of masses and the gain in humidity or the lack of humidity in some areas. We can see also there's a decadal phenomena on the sea level rise here. Here you can see the sea level rise from the beginning of the Industrial Revolution up to now. Okay. So basically in pink you have measurement made by tide gauges, and from here, the last part, you can see measurement taken from space. Okay, and you can see that the measurements are agreeing, and this means that we can now have a very global picture about the sea level rise all over the oceans from satellites. But we need to calibrate these measurements by also local measurements made by tide gauges. Here you have the sea level variation in the Pacific Ocean here. And you can see on the black dots are the tide gauges, and the color here are from measurements made by satellites. There is a lot of how to say of causes for this rise of the oceans. Of course, one of the main causes are due to the melting of the ices on the polar caps. But you need, as I said, to control this on a global basis. The key word here is global, because when we cannot separate, how to say, the climate in the South Pacific from the climate on other parts of the on the planet. It's possible on a very short time scale. That is to say, if you want to predict 1 year in advance, 2 years in advance, maybe you can do some separation. But if you want to compute for, how to say, 1 century, you need to take into account the whole planet, because basically the planet is one, and basically, for example, the mixing of the atmosphere, the total mixing of the atmosphere is something like 2 weeks, 1 month maximum. The global mixing of the oceans is 2,000 years, but the upper layer of the oceans basically is something between weeks and 10 years. Okay? So basically, you cannot predict the climate accurately over 1 century only on the South Pacific basin. You need to look at the whole planet. You cannot separate. So, as I said, why we need Geodesy Observatory? Because we need to survey the moving superficial layer of the Earth, and these data are ultimately going to the IPCC. And as I said, Geodesy specializes in the modeling of the shift of the masses all over the Earth. And we are able to look at the transport of masses through the tiny modification induced in the gravity field of the Earth, the tiny modification induced in the rotation of the Earth, and also by doing measurement of the sea level variations. There is also one thing that is difficult to understand for people that are not involved on this, is we need to refer these motions to a given reference frame. Because basically, if you look at the wind, if you look at the currents, you need to say there is a current, okay, at a few kilometers per hour, but with respect to what? So you need to have some reference that is stable or can be computed accurately within time frames of 1 century. And this is called the ITRF, International Terrestrial Reference Frame. Here we have all the signals that are taken into account by a Geodesy Observatory. As I said, it's a lot of techniques. I have no time to discuss them in details, but basically the main are about geometry, as I said, position and motion of the station, Earth rotation, and gravity. And here you have all the phenomena that are impact these measurements. Oops, sorry. Okay, that I said is basically we are looking at very, very signals, and we need to refer them to a reference frame. Okay, and one of the tasks of Geodesy of the observatory is to maintain as accurately as we can this reference frame. For example, let me illustrate here. Here you have the Earth. You know that the Earth is made of plates. There's a plates are sliding all around the world. With here, for example, we are going to Japan with a velocity of 7 centimeters per year. So we need to measure this. We have also vertical motions. For example, here, the island of Tahiti is going down with a velocity of is about 0.3 millimeters per year, because we are sinking in the Earth's mantle. So we need to be able to measure this. So we need a coordination of this Geodesy Observatory, because, as I said, there are global observations. So we need to have a coordination between Geodesy Observatory. You cannot do your own measurements and do your own interpretation. That's completely useless. So you need to feed your measurements to upper levels that will integrate them, and thereafter they will calibrate them, and thereafter at the end this measurement will go in the climate models. So this is done under the GGOS. GGOS is a global geodetic observing system that is maintained by the Association of Geodesy. And this is particularly important because you are using standards. Standards meaning calibration processes the way to present the data, the way to calibrate the data are the same for everyone, for every geodesy observatory on the Earth. So at the moment, you can see Geodesy Observatory, here is Tahiti, and you can see why these observatories are extremely important, because we have one in Tahiti, one in Hawaii, and a small one is Eastern Island at the moment. Okay, in Australia, and you can see most of them are, to say, overrepresented over Europe and over the US. So Tahiti has become a fundamental geodetic reference frame. It's about 20 years old right now. We have many techniques implemented here. So again, a lot of things that are highly technical. It's not an astronomy observatory, so it's very simple to say, people, we are observing the star. Here, no. We are observing satellites. We are observing very tiny phenomena by very sophisticated techniques. So basically, at the moment, we have a laser station, several GPS, several Dory station is all about tracking of satellites. And you are also maintaining a small network of tide gauges all over French Polynesia. So you can see here the laser firing at night. So if you are interested in, we can ask the people involved in the technician. So you can have to say, look at what is the laser operating. Here you can see what is the principle of the laser. Here, for example, we have a satellite. Satellite, there is a radar. So the radar is sending waves, doing ping pong here. Okay, so you have the altitude, the sea level with respect to the satellite. But you need to know where the satellite is. And the satellite is tracked from the laser station. There is one in Tahiti here. We have several GPS that are doing the same with radio waves. This is another one with the called Doris. And as I said, we are maintaining tide gauges all over French Polynesia. Here you have a typical tide gauges. These tide gauges in the Australs. And just to illustrate how difficult to do the measurements, for example, here we have the radar here, sending waves here. You are measuring to say the difference of altitude between the radar and the sea. But at the same stage, the tide gauge is going down because the island is basically sinking into the Earth's mantle. So we have to separate the two motion. So here basically is going up with 0.5 millimeters per year, and here it's going down with 0.2 millimeters per year. So we need to have a look at the difference. Oops. It's not operating. Okay. Seems to be frozen. Yeah. Sorry about. Computers sometimes are not appropriate here. Maybe some technician to help. Okay, so anyway, I will finish. It's nearly finished. So basically, I just want to tell you that it is important to maintain this type of geodesy observatory, because as a geodesy observatory are, to say, feeding up climate models with data that are absolutely needed to be able to constrain climate models. Okay, and climate models cannot be constrained by only data from greenhouse gases and temperature. It's simply impossible. So you need this type of data to be able to predict what will happen by the end of the century. And of course, you know that is quite important for some communities. Okay, I stop here. Okay, so question? So.
That was a really good presentation. I really enjoyed it. I'm just wondering about